Okay, so, hello and welcome. In this very interesting session, I'm going to take up uh, how do you find all the solutions to Pythagoras theorem. And if you recall, Pythagorean triplets are all those integers which satisfy the equation x squared plus y squared equal to z squared. Right. So one of the possibly most interesting question that you can ask yourself is that how do you find the total number of solutions of this equation? uh, Dual total number of solutions is infinite because even if there is one triplet which satisfies this equation, we can always find infinitely many triplets which will satisfy this equation. Right. So, in fact, what we are trying to do in this case is that we're trying to sort of find the all the solutions if we can to this Pythagoras theorem. Right. So, how do you begin? So, well, the first simplifying assumption that's going to be is that I'm to assume that the GCD of XYZ is going to be 1. And you have absolutely legitimate right to ask that what if the GCD is not 1? What if the GCD of X, Y, and Z is something else, like something like K? Well, if you find all the solutions to GCD equal to 1, you will be able to find all the solutions to GCD equal to K. All that you have to do is that you have to just multiply the entire equation by K squared and you'll get a new solution. So for example, that if a primitive like 3, 4, 5 satisfies this. So 3 square plus 4 square plus 5 is equal to 5 square, which means that 3, 4, 5 is a solution. So you multiply these numbers by any number k, and that will be a solution. So 3k, 4k, 5k will be a solution because, well, 3k squared plus 4k squared is going to be equal to 5k squared. So the most interesting bit is that how do you get this? How do you get to find all the solutions of this equation? So my first simplifying assumption is that say that the GCD of x, y, and z is 1. Notice that we haven't said that the pairwise GCD of these numbers is 1. We have said that the GCD of 3 numbers is 1. But in this case, that necessarily translates into that the GCD of pairwise numbers must be 1, because think about it. If you say that the GCD of x and y is k, where k is not equal to 1, then it would mean that k square will divide this left hand side, which would mean that k square will divide z square, which means that k will divide z, right? Similarly, you can write x squared as z squared minus y squared. And if you're going to say that the GCD of z and y is d, so d squared divides this number, and d squared divides this number, which means that d will divide x. So what we assumed was that the GCD of x, y, z is 1, but it eventually turned out that the GCD of x and y must be 1, a GCD of y and z must be 1, and GCD of z and x must be 1. So that's that. So pairwise GCD is also 1. So any two numbers chosen must be co-prime, right? Next, we're going to do some parity analysis that uh, can all of these numbers be even? No, in fact, we know that no two numbers can be even, because if two numbers are even, then they have a GCD of at least 2, which we can't afford because we have said that the pairwise GCD is 1. So, which means that exactly two numbers must be odd and one number must be even, or all the three must be odd. You can't have more than one number being even. So we have the two possibilities. So either all the three numbers are odd, or 2 are odd, and 1 is even. So I'll argue that, in fact, 3 are odd is also impossible, because if all these numbers are odd, then we know that this is congruent to 1 mod 8. This is congruent to 1 mod 8. So the square of any odd number is congruent to 1 mod 8. So left hand side is 2 mod 8. However, the right hand side, just 1 mod 8. So LHS is 2 mod 8. RHS is 1 mod 8. So that's not possible. Not possible, in fact. So if 3 odd is not possible, then we are left with only one case, that 2 numbers must be odd and one number must be even. So the obvious question to ask is that which number must be odd and which number must be even. So come to think of it, well, so but we have said that 2 numbers must be odd and one must be even. Can this be even? Well, the answer to that is no, because if this is even, then this is odd and that's odd. So if this is odd, so it must be 1 mod 8. It must be 1 mod 8. So left hand side must be 2 mod 8. But since z is even, so the square of z is going to be either 0 mod 8 or 4 mod 8. So that's not possible, which means that both of these numbers can't be even, both of these numbers can't be odd. So it means that one of them must be odd and one of them must be even. So, all right, so let me take, without loss of, now that we have established that exactly one number on the left-hand side is odd and exactly one of them is even. So let me say that without loss of generality, say that x is even, and y and z are odd. All right, so whereas leave us, so that leaves us to the following point, that x square is equal to z square minus y square, and x square will be equal to z minus y into z plus y. Now have a look at this. So since x is even, therefore x square is even, and these numbers have the same parity. So you can see that z minus y and z plus y must be of the same parity, because their difference is even. Their difference is 2y, 2y is even. And if the difference of two numbers is even, then they must have the same parity. That means that either they must be both even or they must be both odd. Since left hand side is even, so it means that these numbers must be equal. Both of them must be equal. Right, so now at this point, I'm quite tempted to say that, can we say at this point that, well, since the product of these two numbers is a perfect square, so it means that this number must be a perfect square and this number must be a perfect square. Can we say that? Well, the answer to that is no. And for obvious reasons, because 2 into 18 is a perfect square, but neither 2 is a perfect square nor 18 is a perfect square. But if we can prove somehow that these numbers are co-prime, which they're not at this stage, and if their product is a perfect square, then both these numbers must be the square perfect squares, because these numbers are co-prime. So the prime numbers that features here will not feature here, right? Okay, so what we have established is that x squared is even. What that tells you is that this is even, this is even. So see that the GCD of z minus y and z plus y is d, right? Since we know that z minus y and z plus y are both even, so the GCD must be a multiple of 2. It contains 2. we can say that 2 must divide D, right? Because this number is even, this number is even. So the GCD must be even. And any number must be divisible, any even number must be divisible by 2. Next, since D is the GCD of these numbers, so therefore D divides their difference. So D divides their difference and their sum. So which means that D divides 2y and D divides 2z. Because D divides this and D divides that. So D divides their sum. D divides this and D divides that. So D divides their difference. Well, lovely. So what do you get? Well, D divides 2y and D divides 2z. And we know that GCD of y and z is 1 from our earlier assumption. That essentially means that D divides 2. Because come to think about it, that if there is any prime number which is contained in y and that's also contained in D, then D will not be able to divide 2z because y and z are co-prime. And that prime number which is present in D, which was originally present in y, will not be present in z because y and z are co-prime. So D divides 2y and D divides 2z. It simply means that D will divide 2 and there is no other part of y or z which D is going to divide because the GCD of y and z is 1. Oh, well, so what does that tell you? That tells you that the GCD, that tells you that 2 divides D and it tells you that D divides 2. It tells you that, well, it tells you that D is equal to 2. Right, so it means that the GCD of z minus y and z plus y, they are 2. So which would mean that z minus y can be thought of as something like 2 times a, and z plus y can be thought of as 2 times b, where a and b are co-prime. So that equation becomes x square is equal to z minus y, which is 2a, z plus y, which is 4a, 4 into a into e. Right. Now have a look at this. This side is a perfect square. This number is a perfect square. So this number must be a perfect square for left hand side to be a perfect square. And since these numbers are co-prime, therefore they must be perfect squares themselves. You can't have any prime number which is odd in power because that prime number will not be present here because the GCD is 1, and in that case this will not be a perfect square, but left hand side is a perfect square. So that tells you that A must be a perfect square, something like n square, and B must be a perfect square, something like m square. So z minus y must be equal to 2n square, and z plus y should be equal to 2m square. So if you solve this, you'll get z is equal to, in fact, m square plus n square. And you get y is equal to m square minus n square. And since x square was the difference of these two, so x will be equal to 2mn. And there we are. And we have your Pythagorean triplets. So x, y, and z, they're going to be, well, 2mn, m square minus n square, and m square plus n square. And as you keep on putting the different values of m, you'll get different answers. Now to make the answer very general, let's multiply this by a number k, because initially we had assumed that the GCD of xyz was 1. Let's make that correction. So the general Pythagorean triplet is going to be 2kmn, k into m square minus n square, k into m square plus n square. Right, and that's the general solution. All right. So I'm hoping that you liked it.